36 valence electrons, 40, 44, or 50. There's essentially two ways that we can do this. One is to find the molecular formula, and this is not actually the molecular formula of this molecule, it's just an example. Or we can do it with the stick and dot method. Regardless, because our molecule is in bond line form, we may need to convert it into a Lewis structure to reveal the missing atoms and or sticks and dots. If we look up here at this molecule, the ends and the bends are carbons, and they may or may not have hydrogens directly attached to it. Similarly, each of the ends and the bends of our molecule of interest are carbons, so there are a total of 1, 2, 3, 4, 5, 6 carbons total. By nature of its properties, each atom of carbon will form exactly 4 bonds, but it's clear looking at this diagram that none of these carbons appear to have 4 bonds. And broadly speaking, that goes back to the fact that a bond line structure is a summary model. It doesn't illustrate all the features of a molecule. Because each of these carbons does in fact have 4 bonds, it's just that we don't see all of them. Specifically, we only see the bonds between carbon and carbon, as well as carbon and any other atom that is not hydrogen, such as oxygen right here. The carbon right here, for example, has 4 bonds like the rest of them, but we only see one of them. And hydrogens are going to make up the difference. So if this carbon has 4 bonds total and we see one of them, the carbon-to-carbon bond, it has 3 single bonds with hydrogen, 3 hydrogens attached. So we use this equation up at the top right here to calculate the number of hydrogens that each carbon is attached to. And that's what each of these numbers are. For example, this carbon right here has 2 hydrogens attached to it. Now we can fill in the rest with hydrogens and count them up for this molecule. Thus, we can construct our molecular formula. There's 6 carbons, there's 13 hydrogens, 1 oxygen, and 1 chlorine. It just so happens that the group to which an element belongs tells us exactly how many valence electrons a single atom of that element has. So if hydrogen is in group 1, carbon in group 4, oxygen in group 6, chlorine in group 7, that means that a single hydrogen will have 1 valence electron. A single carbon will have 4, a single oxygen will have 6, and chlorine 7. So if a single carbon has 4 valence electrons and we have 6 of them, there's 6 times 4 equals 24 valence electrons that carbon alone contributes. Hydrogen, on the other hand, contributes 1, and there's 13 of them, so hydrogen in total contributes 13 valence electrons. So with carbon and hydrogen alone, we've already accounted for 24 plus 13 equals 37 valence electrons, and we haven't even gone through oxygen and chlorine. So we'll eliminate choice A because it's already too small. We do the same product of quantity and group number for both of the remaining elements, oxygen and chlorine, add everything together, and it comes to 50 valence electrons total for the molecule. So that means that D, 50 valence electrons, is our answer. However, there's another way that we could have done this, and I highly recommend doing it this way if you are taking organic chemistry or plan to very soon. I did mention that we can find the number of valence electrons as a sum of sticks and dots, but where the heck are all the dots? Does this molecule even have any dots? Well, I can assure you that this molecule does have dots, and finding them lies in the fact that each atom has a 0 formal charge. How do we know there are no formal charges? There's no charges? Because no charges are mentioned in our diagram. There's no +1 or +3 or -1. So we can assume that all the elements have a charge of 0. And the good news is that whenever carbon and hydrogen have 0 formal charges, which is basically always, neither of them will have any dots. So that just leaves us with chlorine and oxygen. And we can actually use their formal charges to calculate the number of dots using this equation. This is actually the formal charge equation that's just been rearranged to solve for the number of dots. Oxygen is in group 6. It has 2 sticks in this molecule, and it has 0 formal charge. 6 minus 2 minus 0 equals 4 dots. Whereas chlorine, it's in group 7. It has 1 stick, and it doesn't have a formal charge, so 7 minus 1 minus 0 equals 6 dots. So now we've taken care of the lone pairs, the dots, and we can see every single stick and dot of this molecule. So now we can count them up to figure out exactly how many valence electrons we have. 2, 4, 6, 8, 10, 12, all the way to 46, 48, 50, using this key, this conversion chart that tells us what each of these symbols, the sticks and the dots, represent in terms of the number of valence electrons. Therefore, using both methods got us the correct answer of 50 valence electrons, and I challenge you to try both methods for the same molecule.